Imagine a quiet, unassuming commercial warehouse, maybe in Navi Mumbai or Chennai. No smokestacks, no towering transmission lines. From the outside, it basically looks completely still.
Yeah, just another logistics hub, right?
Exactly. But now imagine that inside that quiet building, there is a continuous electrical load equivalent to a medium-sized steel mill, all packed into a few aisles of silent black cabinets. That is the modern hyperscale data center.
It really is a masterclass in disguise. I
Yeah.
mean, you are looking at the absolute definition of a mission-critical electrical facility hiding right in plain sight. And the engineering stakes inside that building, they're astronomically high.
Welcome to this deep dive. Today, we are analyzing a massive shift happening right now in the Indian infrastructure space. Our mission is highly specific. We are mapping out exactly how you, especially if you're an electrical engineer with years of utility or power sector experience, can translate your existing skills into the booming hyperscale data center sector.
Right. And we have pulled from current engineering briefs, system architecture outlines, and Indian infrastructure market analyses to give you a very practical engineering roadmap.
Okay, let's unpack this. If you are an electrical engineer in India with maybe 15 or 20 years of power system experience, you need to hear this. Because we are not just looking at a passing trend, we are looking at a fundamental shift in where heavy electrical engineering is actually needed most.
Absolutely. To truly understand the scale of this career opportunity, you have to look at the sheer staggering power demand driving it. Data centers are becoming a major infrastructure sector in India because of a massive convergence of factors.
The digital boom, basically.
Exactly. We are seeing the explosive growth of cloud computing, the nationwide rollout of 5G, and strict data localization policies requiring data to actually stay within the country. Add to that the aggressive digitalization of the BFSI sector: banking, financial services, and insurance.
Not to mention e-commerce, enterprise applications, and massive government digital infrastructure projects. All of this digital data requires physical space, and more importantly, physical power.
Yes. The power densities are just going through the roof.
But see, I look at a data center, and I just see a giant air-conditioned warehouse for hard drives. If I have spent the last 15 years building 400 kVA substations for the grid, working with massive transformers and high-voltage switch yards, why on earth would I want to go work in an IT building?
Right. I hear that a lot from utility guys.
I mean, why does a facility like that need someone with heavy, high-voltage experience?
What's fascinating here is that the IT equipment, the servers, the hard drives, is actually just the tip of the iceberg. A hyperscale data center is not an IT building. It is fundamentally a mission-critical electrical facility that just happens to house computers.
So the scale is much larger than people realize.
Oh, absolutely. Think about what it takes to keep thousands of servers running without a single millisecond of interruption. 24 hours a day, for years. You are dealing with high-voltage incoming utility supplies. You have major gas-insulated switchgear, or GIS installations.
Right.
You are managing massive step-down transformers, medium-voltage switchgear, incredibly complex protection schemes, and massive DG sets diesel generators. We are talking about campuses that require 50, 100, or even 200 megawatts of continuous power.
That is literally the load of a small city.
Yes, it is.
And the engineering math is changing rapidly because of artificial intelligence. According to the architecture outlines we were reviewing, AI and GPU computing are radically pushing up power density.
Yeah, GPUs are incredibly power hungry.
Exactly. We are seeing rack densities, meaning the amount of power consumed by a single cabinet of servers hitting levels we have never seen before, which completely alters the grid connection requirements, forces heavy upgrades to the electrical distribution, and even demands advanced liquid cooling directly at the chip level.
Exactly. AI doesn't just need more power. It needs it delivered in a much more condensed physical footprint. To really see where the electrical engineer fits into this new reality, we should trace exactly how power flows through this facility. Let us follow the electron's journey.
Let us trace it. It starts at the utility grid, coming in at high voltage, say 132 kV or 220 kV, maybe even via a massive HVDC transmission link from a renewable park before it is inverted to AC at the boundary.
Right, and then it hits the high-voltage switchgear, either GIS or AIS, depending on the land availability.
Correct. From there, it goes through the primary transformers and steps down to the medium voltage switchgear. This is where it interfaces with the backup generation, the DG sets.
And that MV level is critical. From there, it flows downstream to the uninterruptible power supplies, the UPS systems, which ensure the power is perfectly clean and absolutely continuous.
Then it moves through the ATS or STS to transfer switches into the power distribution units, or PDUs.
Right, stepping down to LV low voltage.
From the PDUs, it travels down overhead busways, into the remote power panels, or RPPs, then to the rack-level PDUs, and finally into the server's CPU, or GPU.
And at every single stage of that chain, from the massive utility interconnection at the boundary wall, all the way down to the rack-level power distribution, you need experienced electrical engineers.
You cannot just plug this into a wall socket.
Not at all. You need professionals to handle the earthing grids, the lightning protection, the power quality analysis. You need engineers running the SCADA systems, handling the complex electrical commissioning, and managing the ongoing operations and maintenance.
Here's where it gets really interesting. When you look inside the modern server rack, you don't just see a single power cable. You have A-side and B-side power feeds.
The dual path.
Right. The IT equipment actually has dual power supplies. It is exactly like a critical hospital life support system. If one heart fails, another is already pumping perfectly in sync, completely independent of the first, feeding from an entirely separate electrical path.
That dual path design is the bedrock of data center reliability. But it brings us to a major question for you, the listener. If you were sitting there with 10 or 15 years of experience in transmission, distribution, power generation, or heavy industrial electrical systems, you might be asking yourself, do I have to start my career all over again to get into this space?
And the answer from the industry is a definitive no. If you come from a substation background, this part will be very familiar. Think about your existing toolkit.
It is huge.
You already know how transformers operate. You know switchgear, GIS, and how to program and interrogate protection relays. You deeply understand CTs and PTs, fault analysis, earthing systems, and power quality.
Basically the entire upstream infrastructure.
Exactly. You know how to operate SCADA systems, how to execute high-voltage switching operations safely, and how to manage control room operations. You test, you maintain, you ensure electrical safety.
That existing knowledge is incredibly valuable. Your foundation in Ohm's law, short circuit calculations, and heavy equipment operation is highly transferable. You do not need to relearn how electricity works. However, to make the jump successfully, there is a layer of new critical facility knowledge you must acquire.
Right. But there are some data center-specific systems you must learn. Let us break those down. What is the gap between a utility engineer and a data center engineer?
First, you need to master UPS systems. You need to understand how a double conversion UPS takes AC power, rectifies it to DC to float the batteries, and then inverts it back to a perfectly clean AC sine wave for the servers.
And battery chemistry is changing too, right? Lead acid to lithium ion.
Oh, absolutely, which changes the safety and thermal profiling entirely. Next is DG paralleling.
Hold on, I want to pause on DG paralleling. Why is that specifically called out as a difficult hurdle for newcomers? Generators exist in heavy industry too.
They do, yes. But in a hyperscale data center, you might have 20 massive diesel generators that all need to start automatically, synchronize their frequency, match their phase angles, and parallel onto a common bus, all within maybe 10 to 15 seconds of a grid failure.
Wow. 15 seconds for 20 generators.
Exactly. If the synchronization is off by even a fraction of a phase angle, the mechanical forces can literally tear the alternators apart. Managing that automated sequence is a highly specialized skill.
That makes sense.
Beyond that, you need to understand transfer switches, ATS, and SPS.
STS being the static transfer switch.
Yes, the STS is fascinating. Unlike a mechanical ATS breaker that takes time to physically open and close, an STS uses solid-state thyristors. It can transfer an electrical load between two entirely different power sources in about 4 milliseconds.
4 milliseconds.
Yeah, the servers never even register that the power source changed. You also have to learn the downstream distribution, the PDUs, the RPPs, and the busway system.
And the topologies, right.
Most importantly, yes, you have to understand the specific topology of a data center. You need to learn the practical engineering differences between N+1 and 2N redundancy, the concept of concurrent maintainability, and true fault tolerance.
Okay, I have to stop you there because those terms get thrown around a lot in engineering circles. Redundancy, I understand. Having a backup generator is redundancy. N+1 means you need 4 units to carry the load, so you install 5.
Correct.
But concurrent maintainability is a different beast entirely. Let us look at this from a practical engineering point of view. What does concurrent maintainability actually look like on a Tuesday afternoon when a primary breaker fails?
That is the perfect scenario to illustrate it. This raises an important question about how these facilities never go offline. See, redundancy just means you have spare equipment sitting there. Concurrent maintainability means the facility is designed so that you can physically isolate, shut down, pull out, and perform heavy maintenance on any single electrical or mechanical component in the entire facility.
And the servers keep running?
The IT load will never drop. If a main MV breaker fails on a Tuesday, you can isolate that entire switchboard. The A-side power drops, but because the system is concurrently maintainable, the B-side power pass automatically takes the full load. No servers go offline.
And what about fault tolerance?
Fault tolerance goes one step further. It means the system can automatically sustain a completely unexpected, catastrophic failure of a component without any human intervention, and the load remains perfectly stable.
Designing a system where you can safely rip out a 33 kV breaker for maintenance while the building continues to draw 50 megawatts is just an incredible engineering feat.
It requires extreme precision in design.
But wait, if we are pumping 50 megawatts of power into a confined room of servers, the sheer physics of electrical resistance means almost all of that power is being converted directly into heat. How does the room not catch fire?
That is the big question.
Which brings us to the cooling. Why must a pure electrical engineer deeply understand chillers and liquid cooling if they are an HVAC engineer?
Because in a data center, the electrical and mechanical systems are entirely interdependent. The golden rule of data center engineering is a simple equation. IT load equals heat, which equals cooling load, which ultimately equals electrical load.
Ah, so it all comes back to the power draw.
Exactly. A data center is an integrated organism. When you have massive chillers, cooling towers, primary and secondary chilled water pumps, CRAH units, which are computer room air handlers.
Basically, massive industrial air conditioners on the data floor.
Right, and CRA units and CDUs, or coolant distribution units for direct-to-chip liquid cooling, those are all massive electrical loads.
I see. If the power to the chilled water pumps fails, the cooling stops instantly.
Instantly.
And with the density of AI servers, if the cooling stops, the servers will overheat and thermal trip in a matter of minutes, sometimes seconds. So the electrical engineer is ultimately responsible for keeping the cooling alive, and you manage all of this through the facility's monitoring systems.
Visibility is everything. You cannot manage what you cannot see. In a utility substation, you rely heavily on SCADA. In a data center, you have SCADA for supervisory control, but you also have the EPMS.
The electrical power monitoring system.
Yes. You also have the BMS, the building management system for the mechanical and HVAC side. And you have DCIM, data center infrastructure management, which aggregates all this data. Even life safety systems like VIVDA, very early smoke detection apparatus, are tied into this nervous system.
How does the data actually flow up to the operator?
The conceptual architecture throws from the field equipment, the breakers, and relays up to the IEDs, PLCs, or smart meters across the network into the SCADA or EPMS, stored in a data historian, fed into the DCIM, and finally displayed visually in the control room.
I like to think of the EPMS as the flight instruments in an airplane cockpit. It doesn't just show you where you are right now. It tells you exactly what is going to fail next. As an electrical engineer in that control room, you are monitoring voltage, current, active megawatts, reactive power frequency, breaker statuses, protection alarms, and the exact state of charge on your UPS battery banks. You are watching the sequence of events and power quality trends in real time. Power usage effectiveness, or PUE, is basically your daily scorecard.
That level of monitoring is essential because you're operating at the edge of physics. But to truly appreciate how all these systems, the heavy power, the chilled water cooling, the automated controls harmonize, we have to look at what happens when things go completely wrong.
Let us take a real-world example, the ultimate test of a data center's engineering. A hyperscale data center completely loses its utility source. The external grid goes black. Walk us through exactly what happens in the control room.
It is a high-stakes scenario that unfolds in milliseconds. First, the utility failure is detected by the protection relays. Within a fraction of a second, the MV switchgear responds. The relays trip the incoming breakers to isolate the facility from the dead grid.
Otherwise, your generators would try to backfeed power into the city grid, which would be catastrophic.
Right, you have to island the facility.
Makes sense.
Simultaneously, the automation sends a start signal to the diesel generators. Now, those massive engines take maybe 10 to 15 seconds to crank, start, synchronize, and come up to full voltage.
So what happens during that 15-second gap?
During that critical gap, the UPS systems seamlessly ride through the failure. They instantly switch to discharging their massive battery banks, keeping the AC power flowing to the IT load, perfectly stable.
Servers have no idea the grid just died.
None at all. Once the generators are paralleled and ready, the ATS or STS executes the source transfer, shifting the facility's load from the depleting batteries onto the stable generator bus.
And the cooling.
Throughout this entire sequence, the EPMS is flooding the control room screens with alarms and sequence of events logs. The operators must rapidly analyze this data, verifying that the automation did its job. Crucially, the power to the mechanical cooling systems, the chillers and pumps, must be maintained or rapidly sequenced back on to ensure cooling continuity.
Because if the chillers don't restart, the servers fry anyway.
Exactly. Because of all this orchestrated automation, the IT load experiences continuous uptime. And then, once the utility grid is stable again, the entire process has to happen in reverse. You synchronize the generators back to the grid before transferring the load back, ensuring a bumpless return to normal operation.
Think about how many engineering disciplines have to execute perfectly in those moments. You have electrical, protection, controls, SCADA, mechanical, and operations all interacting flawlessly.
It's a symphony of engineering.
This is why protection engineers have such a huge advantage here. They understand selectivity and coordination, ensuring that if a single server power supply shorts out, it only trips the rack breaker and doesn't cascade up and trip the main MV switchgear. Utility grid protection is one thing, but data center facility protection is an entirely different level of precision.
And we cannot discuss this without mentioning the commissioning engineers. Before a hyperscale facility ever goes live, it goes through an exhaustive testing process.
Right, the FAT and SAT.
Yes, factory acceptance testing, site acceptance testing, and functional testing. But the ultimate hurdle is IST integrated systems testing. During IST, commissioning engineers literally simulate these exact blackout failures.
They just pull the plug.
They pull the plug on the utility, they fail a generator mid-operation, they trip an MV breaker, they simulate a primary cooling failure. They do all of this just to prove, beyond a shadow of a doubt, that the facility's fault tolerance works as designed. It is one of the most intense and dynamic engineering roles in the industry right now.
This is where electrical engineers have a major opportunity. The demand for professionals who can design, build, commission, and operate these fault-tolerant systems is skyrocketing across India.
It is unprecedented growth.
If you look at the job landscape in our sources, the major markets are booming. We are talking about massive multi-megawatt campus developments in Mumbai, Navi Mumbai, Chennai, Hyderabad, Delhi NCR, Pune, and Bengaluru.
The ecosystem of companies hiring is vast.
Yeah.
You have the hyperscalers themselves, companies like AWS, Microsoft, and Google. You have the major data center operators, STT, GDC, Yotta, TTRLS, and others building huge footprints in India.
And they cannot build them without EPCs.
Exactly. Building all of this requires massive EPCs and engineering firms. Companies like L&T, Tata Projects, Schneider Electric, and Siemens are constantly looking for heavy electrical talent to execute these builds.
Now comes the interesting part for electrical engineers, the actual roles. You could be a data center electrical design engineer or an electrical design lead running complex power system studies. You could be a project or construction engineer managing the MV and HV equipment installation on site.
Or a mission-critical commissioning engineer running those blackout IST simulations we just talked about.
Or you could be a critical facilities O&M engineer running the shift in the control room. It is worth noting quickly that our sources are clear on this compensation varies wildly.
It really does.
It depends on your specific experience, whether you are in Mumbai or a Tier 2 city, whether you are with an operator or an EPC, and your shift responsibilities. There are no blanket salary guarantees, but the growth curve is undeniably steep.
The transition pathway to get there is very logical. We can break it down into a practical roadmap for a transmission or substation engineer looking to make the jump. First, you have to understand hyperscale architecture, how the blocks fit together.
Step 1. Got it.
Then, you dive deep into learning UPS systems and the mechanics of DG paralleling.
From there, you move downstream. You master the ATS, STS, PDU, and busway distribution, and then you have to bridge the gap between heavy power and automation by learning EPMS and SCADA from a facility perspective, not just a grid perspective.
Exactly. Then you tackle the conceptual frameworks, deeply understanding N+1 versus 2N redundancy architectures. You must learn the cooling fundamentals because, as we established, you cannot manage the electrical load without understanding the thermal load.
What about the design standards?
Next, get familiar with the governing standards. You don't need to memorize them, but you need to know that TIA 942 and EN 5600 guide the data center design, IEC standards govern your switchgear, and NFPA dictates your electrical safety. Finally, you study the commissioning process and begin building practical project knowledge.
So what does this all mean? If I'm sitting here with 15 years in the utility sector, looking at this massive wave of data center construction across India, how should I frame this in my mind?
If we connect this to the bigger picture, the message is incredibly empowering. You aren't abandoning your engineering career. You aren't starting over from scratch. You are extending your heavy power system expertise into one of the fastest growing mission-critical infrastructure sectors in the world.
The core physics haven't changed.
Exactly. The core physics of Power Ohm's law, induction, fault currents, hasn't changed. The application has just become exponentially more critical and exponentially more dense.
India's digital future doesn't just rely on software engineers writing code in Bengaluru or Hyderabad. It desperately needs heavy electrical engineers who can design, build, protect, and maintain the immense physical infrastructure that actually keeps that digital world running.
It is a critical time to be in power systems. The endpoints of the grid are becoming more powerful than ever before.
Which leaves us with a final thought to mull over, building on everything we have discussed about power density and the electron's journey. With AI pushing rack densities to extreme, unprecedented limits, and our traditional power grids becoming increasingly constrained under the weight of this massive industrial demand, it makes you wonder about the future.
It certainly does.
Will the hyperscale data centers of tomorrow eventually have to become their own independent microgrids? Will they be forced to generate their own continuous baseload power, completely detached from the traditional utility grid, just to guarantee their own survival? It is a fascinating engineering challenge on the horizon. Until next time, keep looking at your skill matrix in a whole new light.